Hey, what's up guys? Today we will learn about chapter 2, free vibration of single degree of freedom. In this chapter, we will learn about free vibration terms and ways to solve the question. So, basically, what is free vibration? Free vibration is a type of vibration in which a force is applied once and the structure or part is allowed to vibrate at its natural frequency. There are two methods that can be used to solve free vibration question. The methods are first, second Newton's law, and the second one is the energy method. In second Newton's law, there is 4 cases that can be analyzed: no damp, under damp, critical damp, and over damp. But as for the energy method, there's only one case, no damp. So, let's take a look at the first case, no damp. In this case, there is formula about equation of motion and time response of displacement. Next, let's take a look at the rest of 3 cases. These 3 cases have dampers, so in the equation of motion have Cx dot but different in time response of displacement. Case 2, where zeta is less than 1, critical damp, zeta is equal to 1, and over damp, zeta more than 1. Next, let's take a look at damping ratio, where zeta is equal to C over CCR, where C is the actual damping and CCR is the critical damping. Another important thing that you need to know is logarithmic decrement. Logarithmic decrement is the sinusoidal graph that is produced in the free vibration chapter. The one cycle represents peak to peak, where T represents time, and x of t represents time response of the displacement. As for the logarithmic decrement formula, they have 3 different formulae which is related to zeta and omega n and also Td. Where n is the number of cycle, x1 the displacement, and Td is the period of damp vibration, which also mean T2 minus T1. So, for more understanding, let's take a look at the first example. Here is the question, and the question asks you to find the natural frequency. First, you must draw the free body diagram and the motion rotate anti-clockwise, so the spring will expand. To draw the forces of the spring must be in the opposite direction. In energy method, there will be 2 main equations. First is the kinetic energy and another one is the potential energy. So in this question, kinetic energy have 2 equations. First is the linear displacement from the mass and another one is the rotation from the pulley. And potential energy only have 1 from the spring. To get the equation in terms of acceleration, you need to differentiate the equation in terms of time. So as for T1, the equation of acceleration is mx dot x double dot. So as for T2, the acceleration equation is I theta dot theta double dot. And for the last equation, which is the potential energy, the acceleration equation is kx x dot. Equate all the equation into 0. Then you can convert the translation x to rotational theta. Now your equation will be in terms of theta only. Note that theta dot is not equal to 0. That means mr squared theta double dot plus I theta double dot plus kr squared theta is equal to 0. Then you must divide all equation in terms of mass. Now your final equation is theta double dot plus kr squared theta over mr squared plus I is equal to 0. Then substitute the value of I equal to half mr squared due to the mass moment inertia of the pulley. After substituting, your final equation will be theta double dot plus 2k over 3m theta. And your omega n is set to k over 3m. Now, let's compare with the second Newton law method. The FBD will be the same as the energy method, but in second Newton law method, you must have kinetic diagram to represent first rotation and linear displacement from the mass. Summation of moment from FBD is equal to summation of moment from kinetic diagram. Equate all forces from the FBD. You can know that the value of mg is equal to k delta. Now you can replace mg with k delta, and k delta can be cancelled out. And your equation will be I theta double dot plus mr squared theta double dot plus kr squared theta. Now divide all equation in terms of I plus mr squared. And your final equation will be theta double dot plus 2k over 3m theta is equal to 0. And you will get natural frequency is set 2k over 3m, which is the same value for both methods. Now, let's see with another example. In this question, it asks you to determine the differential equation of motion by using the generalized coordinate to calculate damping ratio, damp natural frequency, stiffness, damping constant, natural frequency and free vibration solution. Now you know that in this question have damper. So since the diagram rotate anti-clockwise, the damper will expand. So to draw the forces of the damper must follow the rule for spring, which is the opposite side of the action. Then equate all moment is equal to I theta double dot. Multiply the forces with the length to get the moment for each forces and then equate to I theta double dot. Then convert all x in terms of theta. Then divide the equation with mass moment of inertia and your equation will be theta double dot plus CL squared over 16 I theta dot plus 9KL squared over 16 I theta. Then substitute I with 7 over 48 ml squared and you will get theta double dot plus 3c over 7m theta dot plus 27k over 7m theta is equal to 0. From the given information, you can get the value of x1, x2, t1 and t2. From x1 to x2 is 1 cycle, so n is equal to 1. So use logarithmic decrement formula to get the value of delta. The value of delta is 2.1972. Then relate the value of delta with zeta to get the value of zeta. And you will get the value of zeta is 0.3301. Then use the value of T2 and T1 to get the value of TD, period of damped vibration, and the period is 0.05 seconds. Next, you can relate the value of zeta and TD to get the natural frequency of the system. The natural frequency is 133.123 radian per second. Then you can use the formula from the natural frequency to get the value of damped frequency. The value of damped frequency is 125.661 radian per second. From the equation of motion, omega n is equal to sec 27k over 7m. Then relate the value of omega n and m to get the value of k, which is 22.972 kn per meter. Then relate the value of 2 zeta omega n equal to 3c over 7m to get the value of c, and the value of c is 1.025 kns per meter. Since zeta is equal to 0.3301, it means that the value of zeta is in underdamped condition. Use the equation of time response displacement for underdamped condition. Then substitute the value of t which is equal to 0 to get the coefficient of A1, and you will get coefficient of A1 is equal to 0.1. Then use the product rule to get the equation below, which is theta dot t. From the equation, when t is equal to 0, you will get the coefficient of A2. Substitute the value of zeta, omega n, omega d and A1 to get the value of A2, which is 0.035. And you will get the final equation of theta in terms of t by substituting the value of zeta, omega n, A1, omega d and A2. This is the summarize for the formula for the whole chapter 2. Thank you for listening. And good luck for your final exam.